We've seen df dx and we've seen d dx. So now we're going to think about just dx. This sort of object is called a differential. And I really want to emphasize, we're talking about dx, not d dx, right? We thought about that a little bit already, right? As an operator, this is the thing that does the differentiation. This object is what we're going to study right now. It's called a differential. But what does that even mean? Geometrically, these differentials, so dy and dx, represent some change in the linear approximation that I get using the tangent line. So here I've got some function that I've graphed, y equals f of x, and here's a point x, f of x, and I've drawn the tangent line to the curve there. And here's some change in x, which I'm calling dx, and here's some change in y, which I'm calling dy. And if you think about what is the derivative? Well, I mean, the derivative really is dy over dx, right, in some sense. You know, if you take the derivative and multiply it by how much the input changed by, I mean, you don't actually get how much the output changed by, but you get an approximation to how much the output changed by. And that's what this dy here is being used as. This dy is the change in the linear approximation. Okay, here's a statement in words. In words, dy is a change in the linearization or the linear approximation or the tangent line approximation to this function that you're thinking of as y depending on x. That's what dy is. I should emphasize that your dy's had better include a dx in there somewhere. At different points in your life, you'll develop different ideas about what dx and dy really mean. So in a calculus class, in this calculus class, if you really want to, you can think of dx and dy as infinitesimal quantities, very small quantities. It's difficult to make this sort of thinking entirely rigorous, but that's certainly an okay way to think if you're trying to get some intuition for what these things are representing. Now, later on in your life, when you take some course, say a differential geometry course, dx will then be given some better foundation. Right? Dx will be revealed to be a differential form or a covector. I mean, you'll have some actual interpretation of dx. But for the time being, you know, if you really want to, you can regard these things as infinitesimal quantities. But honestly, I wouldn't worry too much about how to actually think about these things. I'd focus more on how to compute with these objects. The basic trick is that if y is f of x, then dy is the derivative of f dx. And you don't even need necessarily to differentiate f in a lot of cases. The differential satisfies many of the same rules or analogous rules as just differentiation satisfies. So for example, d of u and v, or u plus v I should say, is du plus dv. D of u times v, as a product rule, is du times v plus u dv, right? There's a quotient rule. I mean, these differentials satisfy all the same, or I should say analogous rules to derivatives. Let's take a look at an example. For example, maybe y is something easy like x squared, and in that case, what's dy? Well, dy is the derivative 2x times dx. And yes, this does relate some change in x and change in y in terms of linearizations. But you don't even necessarily need to write it this way. You could, if you wanted to, write dx squared and then think that there's a power rule for differentials just like the usual power rule, which then says that this is 2x dx. Or in general, d of x to the n will be n x to the n minus 1 dx. We can cook up a more complicated example. For example, let's calculate d of x sine x. Well, this is d of a product, and I can compute that by using the product rule for differentials. Right? What does that tell me? Well, it'll be d of the first thing times the second thing plus the first thing times d of the second thing. Now, instead of writing dx times sine x, I could write that as sine x dx. And what's d of sine of x? Well, this is d of a function. And remember, how do I take d of a function? Well, it's the derivative times dx. So this is x times the derivative, which is cosine x, times dx. Now, if I like, I could factor out the dx, and I could write this as sine x plus x cosine x dx. Now, of course, I haven't done anything new here, right? I mean, I could have just differentiated x sine x, but the point is that I'm writing it down without ever taking derivatives. I'm sort of using the rules for how to compute differentials, right? Like the differential product rule and the fact that the differential of a function is the derivative dx. Now, I'm being a little bit vague about how to deal with these differentials at this point, but we're going to be seeing more of these differentials in the coming weeks.